Alright, so we're going to do the linear inverted pendulum model. Walking.
Is it just simple?
Very simple. So we have point mass again. Stick with the point foot for now. And what will make it all linear is the constant center of mass height. Okay. So you got the ground, you got your center of mass somewhere up there. You got your foot somewhere there. Okay, since it's point mass, doesn't really matter what mechanism you have between the ground and the foot, as long as it's can keep the center of mass at a constant height. All right. So the force has to lie along the line between the center of mass and the center of pressure of the foot. Since we're constant height, let's call this distance here z naught. And then let's call the location of center of mass x. It's either in the location of the foot, x of the foot. Okay. So, the way I like to derive the equations of motion for this is to look at the components of the force vector. So there's going to be some vertical force Fz, some horizontal component Fx, and so what does Fz have to equal?
The weight of the center mass.
MG.
Yep. Yep, the weight of the mass, Mg. Okay. Now, what's neat about this? What's neat about these two triangles?
They're similar.
They're similar triangles. So this angle equals that angle, this angle equals that angle, and because of that, we have that divided by that equals that divided by that. So Fx over Fz, which is mg, equals x minus x foot divided by center mass height z naught. Okay, so we solve for Fx. Now give us mg over z naught times x minus x foot. All right, and Fx is going to equal mx double dot, right? F equals ma. We'll equal all that. So m divides out, so you get x double dot is g over z naught x minus x foot. And that's your equations of motion for the linear inverted pendulum. Okay. Another way you could come up with the same answer is to say that it's a fixed pendulum rather than moving at a constant height. Say it's a constant leg length, and then you get sine theta in there, and then do the linear approximation of theta, and you get essentially the same thing.
In this case, you're saying x is positive to the left? unless you
No,
switch
let's do x
coordinates?
positive that way, z positive that way.
The negative
So
sign
right
is-
in this, as I have it drawn, x is less than x foot. So this is going to be a negative number. So x double dot is going to be negative, so it's going to be decelerating. Right, because it'll be accelerating in that direction, in the negative x direction. X double dot.
Okay, okay.
All right. Okay. So, since this is the equation, this is similar to the equations of a mass and a spring system. So if you had a mass connected to a spring constant K and mass M, and this distance x, then you'd have x double dot equals negative kx. Right? Or you could say kx minus the set point of the spring x. Right? So the same equations, g and z naught are constant. X foot would be the same as x. We lost this. So just
All
go
of
this
that?
again. The linear inverted pendulum. Okay. So again, you have x double dot equals a constant, g over z naught times the distance x minus x foot, which is a lot like a spring and a damper. And I think that the camera lost that, so let's do that again.
Well, it's just spring then, right?
Oh, sorry, spring. Mass and spring. So you have a unit mass, m equals 1, connected to a spring with a spring rate of negative g over z naught. Okay. Because normally, if this was a mass spring system, there's usually a negative sign there. Right. Okay. So because of that, you can look at the energy in this system, which is 1/2 x dot squared. So this is unit mass again. So we divided m out of that equation. So 1/2 mx dot squared, so 1/2 x dot squared, minus 1/2 kx squared. So if you have a mass spring system, let's write that out. If you have a mass spring system, your energy is going to be your kinetic energy, which is 1/2 mx dot squared plus your potential energy, which is 1/2 kx squared. Okay, so that's how we get the linear inverted pendulum energy. It's 1/2 x dot squared minus 1/2 k, so k is negative, x minus x foot squared. This will be constant. This will be constant on all the trajectories. So up here, it's positive. Okay, so it's going to be 0 on the stable and unstable eigenvectors. And you can solve for the value. Along these lines, x dot will equal, so you take the 1/2 out, put that over there, take the square root. So x dot equals plus or minus square root of g over z naught, x minus x foot, along these lines. It's a positive solution along these lines, negative along these, just so that you get positive negative slope. Okay, I think we're back to where we lost the video. So now, if we want to, so suppose we're walking along and we're on this trajectory, and we're going to take a step at this point. By taking a step, what you do is redefine x, or change where x foot is, but we'll just keep x minus x foot, so here x equals x foot along this line here. Okay. So you're redefining x minus x foot, but you're not losing energy. So with the linear inverted pendulum model, there's no impacts with the ground. You got a constant, your center mass is not doing something like this where it gets an impact there and loses energy. Since it's flat, there's no impacts on the ground. It's just a perfectly smooth transfer. So what you're doing is taking a step out to here somewhere, and what we're going to do is solve for this point such that when you're now on this new trajectory, you get a desired apex velocity. Apex meaning when your pendulum is on top. Okay? Okay, so we know what x currently is, x sub n, what x dot currently is, and we know what our desired apex velocity is going to be. So, when we take this step, x dot is going to be preserved, right? Current position does not matter, right? Because we're instantaneously taking a step, so that won't even come into the equation. So we're looking at what we want our linear inverted pendulum to be. So V desired, well, we know that just from V desired, it's going to be 1/2 V desired squared. So at the apex, right here.
So it's confusing because in bouncing studies, apex is the height between two steps, and here we're talking about when we are directly over the stepping point on the ground.
All right, so what should we call that?
It's
Top of pendulum.
It's the apex because
It's
it's
still
the
the highest
highest.
height.
It's actually the
point.
Well,
You're
the
reaching
height's
and we're
inverted
fixing
pendulum,
Z anyway, so.
Yeah, the height's
Next.
constant.
so-
Let's just call it top of pendulum.
Yep.
Okay, so at the top of pendulum, we'll have a desired velocity. So the linear inverted pendulum at that point will be 1/2 V desired squared. Okay, so that's that point there. But the energy is going to be constant along this whole path. So that's going to be the same as the energy there, which is going to be 1/2 the current velocity, x dot n squared, minus 1/2 g over z naught x minus x foot. Well, I guess so. Okay, so xn will come into play because that's where we're squared. So we're currently here. We're solving for where we're going to put the foot. So let's call it x sub step. Okay. We're going to solve for x step. We know everything else. So we know the desired velocity. We know the current velocity. We know the current position. We know g. We know z dot. And we want to solve for x step. So we can just do that. Let's see here. So put x n dot over here so you can get and get rid of the 1/2s. So g over z naught xn minus x step squared is going to equal x dot n squared minus e divided squared. Okay, and then get rid of this squared by taking square root over here, square root over there, and we'll have to figure out whether or not it's plus or minus in a sec here. Okay, and then well, let's see. And so then finishing solving it, we're gonna get. Let me know if I screw up the algebra here. So xn is gonna x step is gonna equal. Plus or minus. And the plus or minus there. Okay, so x dot n is greater than v desired, so this is going to be positive. X step is going to be where your center mass is, plus, right? Assuming x dot n is positive, then you're going to want to step in front. So the reason there's two solutions is you could solve for either this point, let's see here, this point here or this point here, and we want that point there because we don't want to just go flying off to infinity. We want to actually take the step. That's why there's two solutions, and you just got to be careful about if you take the plus or the minus one.
So which one do we take, or does it matter?
In this case, there's a positive one because we had positive x dot. X dot was greater than v, so this is positive, and we want to step further than we currently are. So I just kind of used logic to reason through it rather than
You want to step
algebra.
in front of where you currently are.
Yeah.
So stepping in front of where we currently are, does shifts us on the graph accordingly, so it's.
Shifts us to the left side of the graph.
Yeah, because what we're doing is this is x minus x foot.
Okay, so we can think of a step as moving the whole graph axis to the right.
Yeah, to the right. Yeah.
And
which
so
is
that's
the
a
same
positive
as-
step.
Yeah.
Okay, okay.
Yeah.
Or because it's consistent between each step, just jumping over on the graph.
Okay, so we would always take the positive root of that when we want to step forward.
No, it wouldn't always be the positive. If you're down here, then you'd have negative numbers and you might want the negative root. It's just that you just take the root that gives you the solution that puts you at the beginning of the trajectory rather than at the end of the trajectory.
Beginning of trajectory.
Okay. So,
What happens with impacts? Oh, sorry, there's no impacts because
There's no impacts.
you're linear.
yep.
For,
All right.
for the apex thing before, since the apex point is the midpoint between two ground, mid-contacts, we could say that the horizontal line itself would be the constant apex velocity even if you had a flight phase. And since the moment you step is, so the top horizontal dotted line you drew in blue,
Mm-hmm.
that would be consistent with what people will later call apex
Maybe,
velocity.
okay. Yeah, let's just call this top pendulum.
Sure, mid-stance or something like that, but yeah, top of pendulum.
Okay. Let's see here. So there's lots of things you can solve for using this linear inverted pendulum as far as stepping, right? So what we solved for was given the state where you need to step to in order to achieve another velocity. You could also solve for things like if I'm going to take a certain step length, so you know this length, and you know your next velocity, when should you take the step?
Right.
Or you can solve for if you know when you're going to take the step and how far you're going to step, what your next velocity is going to be. Pretty much of all the things, of the 3 possible points, choose 2 and you can solve for the third one.
When meaning an event, not measuring time, but just when you're there, that's when you do it.
Yeah.
Okay.
Okay, so let's see here, before, so just a little bit of solving for what the motion would actually look like. So here we're just kind of showing what the x versus x dot are, but what if we want to look at what x versus t is? We want to solve these equations of motion, right? So I'm just going to put the answer there. I'm not going to show how to derive it. Do this. Pretty much anytime you have, so one way of doing it is writing at it as a second order linear system. So d over d of dt x dot is going to equal, so matrix A times x dot. And let's just, as part of linearizing it, you would, set some other variable to equal x minus x foot. So let's just assume x foot is 0 for now. So the derivative of x is just x dot, right? So this is 0, 1. The derivative of x dot is x double dot, which is g over z naught times x, and 0 here because there's no damping in the system. And so you get, let's see here, so then you can write this all out as a big vector, x dot equals big matrix A x, right? And that's why it's called linear inverted pendulum model, because A is constant, so you've got a linear second order dynamic system. If you wanted to solve it for time, you would see that x of t is going to equal x at 0, e to the at, and we're not going to get into the linear algebra of how to solve that. For this particular system, because you do have a saddle point, you end up getting hyperbolic cosines and sines. And just for completion, I'll write down what the equation is. So for x, so x of t equals x naught hyperbolic cosine square root of g over z naught t plus square root of z naught over g x dot at 0 hyperbolic sine square root of g over z naught t. So that's the center of mass position as a function of time. So pretty complicated. Pretty complicated, and what it would kind of look like if you were to graph it is something like this, where suppose you, at t equals 0, you start with a little bit forward angle but no velocity, and then kind of do this, and then you take a, if you take a step here, it kind of looks something like that. And this is, you know, taking a step at that point. And this would be plotting the x minus x squared. That's t, so x minus x squared. And then maybe at the end you take a step to come to a stop. That make sense?
I can't quite see it, but let me just get right there. The four quadrants, coefficients of the A matrix.
Yep.
The one on the lower right was damping.
Yep.
The one on the lower left is?
That's your spring constant.
Okay. And then the upper
And
left
then
right?
these two are just 0 because if you take the derivative of x, it's just x dot. So all you're saying is a truism that x dot equals x dot. Right, is 0 times x plus 1 times x dot.
Okay, and the upper right coefficient represents?
Just that x dot equals x dot,
They're just selection coefficients.
right? Because you're just saying take 0 times x plus 1 times x dot to get x dot.
Okay.
They have no physical implication. They're simply
Yeah.
selection coefficients.
Yeah,
Got it.
it's really
Thank you.
just these that have physical
So it's
meaning,
just
the spring and damper.
Yeah.
The way the matrices are.
Yeah.
Okay.
Yep.
Selection coefficients, spring and
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 the
then
sign
in the sign-
H is this, is that actually flipped from the other places?
What's that?
So all of the square root, they're not all consistent, they're not all square root g over z naught or not?
Well, some are g over z naught and some are z naught over
Okay,
g.
so they are.
So this is your time constant, or 1 over your time constant, because you're multiplying by time. And then this is just a multiplication factor that comes up if you were to actually solve the system.
In the graph there, I'm concerned that that's drawn right and that I understand it.
Yep.
So, can we say, suppose we were at a point standing still, where would we be on that graph? But it's flowing with time.
It's
so-
not, this is an example of walking.
Okay.
So
we're
this
flowing
is
with time, our velocity's lowest
standing
there?
still. Yeah, this is,
That's-
suppose
If you just trace us through events on the plot.
Okay, yep, so this point here would be that you're leaning forward with no velocity, so and somebody lets you go,
Okay.
okay? And then you accelerate a bit to here.
So the vertical axis is speed? Is it position?
No, this is position, sorry. This is
Okay,
X.
okay. So that's
And
x,
this-
not
and
x
this is-
dot.
and this is time. Yeah,
Okay, okay.
okay.
So we accelerate further away from 0 because we were initially leaning, and then we have to take a step.
Yep, then here we take a step to make us now be behind the foot, so negative x,
Right?
okay? And that's gonna cause us to decelerate until we're here, then it'll accelerate again. And so that's why you have these hyperbolic sines and cosines.
So is the derivative horizontal through the midpoint?
No, those,
It's whatever your velocity is.
Your
yeah,
velocity.
this would
Right,
be
Your
your,
okay.
slope is the velocity.
that would be your top of pendulum velocity.
So if we were on one of the eigenvectors, then it would
Then
be
it would
horizontal.
be, yes, and that's what this point is. Then here we take a step onto the stable eigenvector and come
And
to
it
a
levels
stop.
out. Okay.
But all I wanted to do with this is show that hyperbolic sines and cosines are really nasty. You don't want, it's very hard to solve for, and the center of mass trajectories are interestingly shaped because of those sines, hyperbolic sines and cosines. But it kind of makes it hard for planning things and whatnot, which motivates what I'm going to do next, which is first, which is leading up to instantaneous capture point.
Okay.
But to get there, what we'll first do is solve for where to step to in order to come to a stop. So solve for where to step to in order to get onto your stable eigenvector to come to a stop. Okay. So here we solve for given a given a desired velocity, so I guess I can reuse this. Suppose our desired velocity is 0. If our desired velocity is 0, then x step, which we'll call x instantaneous capture point, is where the center of mass is currently, so let's call it x, plus square root of z naught over g times the square root of x dot, which is just x dot. So this is where you should step to, given your velocity and position. Okay? So for human parameters, approximately human parameters, z naught is approximately 1 meter, g is approximately 10, the square root of 1/10 is approximately 1/3, and so, or well, let's call it 0.3, approximately, somewhere around there. Which means that for every meter per second you're traveling, you need to step approximately 30 centimeters forward to come to a stop. Okay, and that makes sense. It kind of works out in real life. If I'm walking at a normal speed, it's about 1.5 meters per second, so I got to step about 45 centimeters forward in order to come to a stop. Okay? If you're in heavier gravity, you would have to take a shorter step because there would be more gravitational, you'd be fighting gravity more, which would be pushing you back more, so you wouldn't have to step as far to come to a stop. And if you're really tall, you have to take a longer step because it's more about the angles than it is about distances. Okay?
No ankle torque.
No ankle torque. This is still point mass, point phi. All right, so this is the point on the ground where if you step to this point with the linear inverted pendulum model, right now, given where you are, your current position and velocity, then you will come to a stop at the top of the pendulum. And yeah. And this comes in really handy because if we write our dynamics in terms of this, it'll be super simplified. So let's go ahead and do that. Okay. So we have x ICP equals x plus square root of z naught over g x dot. So let's differentiate both sides of this. You get x dot ICP equals x dot plus square root of z naught over g times x double dot. Alright, so I just said the derivative of that is derivative of that plus derivative of that. Now we can plug x double dot back in. X dot ICP is x plus square root of z naught over g times g over z naught times x is 6 foot.
So okay. What's
that?
Just to see so we can get it.
Okay. Now you can see what I'm getting at here in that by taking the derivative here, what's going to show up is x ICP again. So to get to that, what we need to do, sorry, this is an x dot.
So make sure we got it. Okay.
Okay.
So it's the square root of z naught over g times g over z naught.
Yep. And which we can simplify right now, which is going to be the square root of g over z naught, right?
Well, wait a minute. Is that right?
Yep. So let's do that.
Is that right? Because z naught is on top under the root sign. It's on the bottom on the outside, right?
Yep.
Okay, so it is root over.
I did right, right?
G
Yeah.
over z naught.
All right.
Okay.
Okay. So now since we want to get XICP back in here, and there's square root of z naught over g x dot, let's just multiply the whole equation by the square root of z over g. Over g, x dot ICP equals square root of z naught over g x. Then that'll cancel this out, so we can get plus x minus x foot, that's plus x minus x foot.
Use an x dot. The first term.
Is x dot, sorry. Okay, and then that's just the XICP, right? So XICP minus x foot. Do that, and then get rid of that square root of g over z naught again to get x dot ICP. So all this is just pretty simple algebra. Square root of g over z naught x ICP minus x foot.
So just copying that. So we have, so the square root of z naught over g times x dot ICP equals x ICP minus x foot.
Minus x foot, yep.
So, okay.
All right, so let me just get rid of the derivation, it's not important anymore, it's just going to together. Okay, really, so here's the definition of XICP, and here is the XICP dynamics, instantaneous capture point dynamics, for the linear inverted pendulum. All right, so now, where originally for the center of mass dynamics we had second order linear system, now we simply have a first order linear system. This is a constant, so the rate at which the instantaneous capture point will move is proportional to the distance of the instantaneous capture point from the foot. And the solution to this is really easy, it's just XICP equals XICP at time 0 times E to all this stuff, sort of G over Z naught. Just T here. I guess this would be XICP minus X foot at 0. No. What am I doing wrong here? Why is X foot? I think, yeah, this would be XICP minus X foot. Okay. So
Within a constant.
within a constant. Let's just so this is T. And so anyway, it's going to be some simple exponential.
No, if t is 0, then you can't have a constant there. That's right. It's the ICP at 0 by definition is ICP of 0.
Right, so when T is 0, this will be 1.
1. So the
So this is
ICP
true.
is 0. So you can't you can't be off by a constant.
Right. I want to say that it's,
You could get enough.
why don't we, let's do this. Let's let P equal XICP minus X foot. So then we still have P dot equals X dot ICP minus X foot dot, which is 0, because the foot's not moving, which equals square root of G over Z naught XICP minus X foot. Let's just P. Okay. you could plug it all back in there. So pretty much just linearized by getting setting x equal to zeros.
And that's on both sides.
Okay, so the distance from the foot to the ICP is going to be its initial distance times e to the g over z naught t, which will just look like that. Okay. And this you can solve for much easier than solving functions of hyperbolic sines and cosines. If you want to do things like, plan ahead and figure out at what time you should take a step so that your instantaneous capture point's in a certain location, things like that.
So now we are stepping by counting time, rather than waiting for a distance event.
What you could do either.
Okay,
Yeah.
okay. So we were saying that at a certain speed that you're running, the capture point is a certain distance ahead of you.
Yep.
So wouldn't the speed of that capture point match your speed of running?
No, your speed,
What's the difference in that
Because the-
definition?
this is what, because right here, this is your speed of your instantaneous capture point, right? Your derivative. It's going to be proportional to the distance from where it is, right? So let's
You're
do-
not
let's
moving
do
at a
an
constant
example.
velocity.
What's that?
You're not moving at a constant velocity.
No, you are not.
Okay, so my velocity is changing and the velocity of the
Instantaneous
ICP
capture
point is changing
Yes.
also.
Yeah.
Okay, so how would you say they move just an intuitive way through a step cycle?
Let's see here.
Do they move together, apart?
No, your instantaneous capture point is going to keep getting further and further away from your point
Until you step.
until you step.
Okay.
So your instantaneous capture point is actually moving faster than your velocity, right?
Yes.
Because it keeps getting further and further away from you.
So at the moment you step or at the moment of midpoint? Okay.
All the time.
So, well, here, this exponential grows, but you're at at time zero, you're at the place where you're stepping, right?
Yeah, so you're
So if
stepping on your instantaneous capture point for the first
Well,
half of your motion. As
if
soon as
you are coming
overbalance,
to a
then
stop.
it starts moving.
But this
Yeah.
hasn't said anything about actually taking a step. So let me just keep going here and maybe
Okay,
I'll answer your
okay.
question.
Sure.
Okay. Before I keep going though, let's point out one thing in that what's nice, another nice thing about it being linear is that x and y are perfectly decoupled. So we can just, add the same equations for y. Y ICP equals y plus square root of z naught over g y dot. Same thing here, we can say that y double dot equals g over z naught y minus y foot. And everything, the two dimensions are completely decoupled. And y dot ICP is going to be the same thing here. Which makes things real nice because since everything's linear and everything's decoupled, you can do overhead views of what's going on using your instantaneous capture point that make a lot of sense, that are much easier to understand, to think about than these sort of diagrams, and much easier to think about than hyperbolic sines and cosines. So let's go ahead and do that. So, pendulum energy anymore. Let's just get rid of it. Okay, so now all we have to deal with is instantaneous capture points. So let's write this vector as a two-dimensional vector. So it has x and y of the ICP. Well, first its definition is just going to be the location of the center of mass, like that, plus, what is it, square root of z naught over g. X dot is okay, and then derivative of that point is going to be z naught So now, that's all we need to think about is these two equations. So suppose we're looking straight down. So x and y now, and z is out of x and y, and z is out of the board. Okay, and this is where our foot is, and this is where our center mass is, and it's moving at this velocity. Then we can use this equation to figure out where our instantaneous capture point is. So it's going to be the center mass position plus some constant times its velocity. So somewhere out here. That's where the ICP currently is. This is where the foot is. This is where the center mass is. Okay? And
Where's the ICP?
all right,
Up there, okay.
okay? So now the velocity of the ICP is going to be along the line from the foot to the ICP in that direction. So the ICP will move along this line, in a straight line. Okay? Let me draw it a little bit bigger and better over here. So center mass moving in this velocity, that's the center mass velocity vector. Instantaneous capture point right there. Let's put the foot down here, make it a little more interesting. Okay. So this line, the ICP will move along that line until you take a step. The center of mass is going to follow this really complicated hyperbolic sine and cosine curve, and eventually asymptotically get to this line until it's collinear with the foot of ICP. And the velocity of the ICP at this point is going to just be this. Square root of g over z naught times this distance. G. So XICP is x foot.
You intend for the ICP to be on the vector between the ICP and the center mass?
The ICP.
Velocity vector. I mean the velocity. That's the velocity of the center
Yeah,
mass.
this should go. Yep, that's collinear.
Okay.
You take the center mass and take a vector, right? Because that's the definition of the ICP: the center mass location plus the x dot center
Velocity,
mass
yeah.
velocity times the constant. So distance.
So, now that we can see it, 'cause you
Yep.
can see it from over here, let's see if I have this right. So, just talking us through, from the placement of the foot,
So your foot's here. Don't assume we're taking a step for this analysis. The
Right.
foot's here and will stay there.
okay.
The center mass started here,
Along
moving in
that
this direction.
velocity, but it'll change moment by moment?
Yep. So the center mass is going to take this path,
Okay, okay.
whereas the instantaneous capture point's just going to take the straight line path.
Does the distance, and the distance between the center of mass and the instantaneous capture point keeps growing as we do this?
It keeps going. Yep.
And
so
the
once,
distance- that
once, so
distance-
if we wait a little bit, once the center mass, suppose we wait till the center mass is here, and its velocity is tangent to its path, then the instantaneous capture point will be here at that point. Right?
Right.
So this is center mass, call it a delta t, here call it 0. This is the instantaneous capture point. This is the ICP at time 0, and this is the ICP at time delta t.
So, the velocity is always tangent to the hyperbolic curve.
Yeah.
The distance between the center
Yeah,
mass
so
and the
this, so
ICP
this,
will keep
this
growing?
distance just grew because the velocity just grew.
Right, so we could parameterize that if I wanted
Yeah.
to graph it out, and we could
Yeah.
pretty much be able to draw this by
Probably,
eye.
so to be more accurate, it would have probably sped up a bit more, so maybe it would have been. somewhere up here. So that this line goes like that. Okay. So really what's kind of going on is you have your two state variables, right? X and x dot or and y dot. And this distance here keeps shrinking. This is exponentially shrinking. This is the kind of the dimension that is stable, right? Where you have a stable eigenvector. This is the thing that keeps shrinking. Whereas this distance is just blowing up to infinity. That's the unstable mode. A lot of people, so another name people have for instantaneous capture point is the, looking at it now. It's been few people came up with it in different ways.
That's
Using
not
different
zero
names.
moments.
No,
No,
no.
it's too-
So foot placement estimator is what some people call it.
Not the foot rotation.
No,
So
not the uncontrollable dynamics, but the divergent dynamics. This is the instantaneous capture point is the divergent dynamics. It's diverging going off to infinity, whereas these are the converging dynamics. So no matter, when you add more and more degrees of freedom, you're still always going to have one that's diverging. That's what makes walking hard and interesting, is that you have one that's naturally unstable. All the others you can stabilize without having to take a step. In order to stabilize the diverging dynamics, you have to take steps.
So the idea is instead of dealing with all of the hyperbolic sines and cosines, you basically push your ICP out in front of you and your COM tracks it.
Yep. So now path planning or walking or all that stuff, stepping over stepping stones is all about just paddling in a point forward, like you're.
So every segment of our path is a hyperbolic segment.
Well, every segment of the center of mass is, but every segment of the instantaneous capture point is a line. So, for example,
what creates that line in the first place? Is that just an artifact of the fact that we're keeping the
it's these two this equation.
Okay, but if we weren't keeping a constant center of mass height, then that would not be linear anymore, correct?
Right.
Okay.
And yeah, it's
Well, your
because this
ICP
equation. It's really because x and y are decoupled. So you get
Yeah.
X and y dot u over d ICP is some constant times x and y. Because of that, it's aligned, right? X and y both grow at the same rate. You could come up with nonlinear equations, which still gives you a line, but you need that x
How
and
you
y to grow at the
follow
exact
that
same rate.
line.
Okay.
Change.
Yeah, I have a
It's-
question.
So you could probably get rid of the constant center mass height thing and find some nonlinear surface where you still have, where you can still solve for an instantaneous capture point that moves along the line.
But it does basically require a coincidental canceling out in order for that line.
Coincidental decoupling of x and y.
Okay.
Question.
Yep.
For an initial velocity, for an initial location and velocity of the COM,
Yep.
just any location and there's a velocity,
Mm-hmm.
I pick an arbitrary foot placement point.
Okay. Yep.
How do I know the hyperboloid and the asymptotic direction it's going to take?
Okay, so you said take a arbitrary center mass position and velocity,
Right? And put my foot
any
down somewhere.
Yep. So now what you want to do is solve for the XICP using this equation. So you have x center mass, you've got x dot center mass. So that will give you the instantaneous capture point right now. Then
Okay,
you
so the
use this
instantaneous capture
equation.
point is ahead on that straight line
Yep.
of that velocity. It's
Straight
on
line.
there somewhere right
Yep, exactly what I drew here.
now. Okay.
And then you take a line from the foot to the instantaneous capture point, and that's the way the instantaneous capture point will move. So
And
then
it's
this guy
hyperbolic
is
from
going to
there.
be hyperbolic from there.
Okay.
And
I'll
never
try.
quite reaching it.
Okay.
Okay? Alright.
So there should be easy draftsman's ways to just draw this by hand once you graph it out.
Yep.
Okay.
Yep. And that's the whole point. And that's what's really nice is this stuff is super fast to compute, real easy to just look at overhead views to see what's going on. And even though our system isn't point mass at a constant height, if you still look at this quantity,
It's gonna oscillate around it, no matter what you do, so it's an
it's,
reference.
well, it still obeys this rule for the most part.
Okay.
If you look at this quantity called the instantaneous capture point for whatever model, and watch what it does with respect to the center of pressure, it pretty much moves away from the center of pressure along a straight line at approximately this rate. Even once you start adding arms and, you know, all this complication to your model. Okay, so suppose we had a bunch of stepping stones, and we're currently standing here, and we want to get to this one. So when you're not moving, your center of mass, your center of pressure, your instantaneous capture point, everything are all on top of each other, right? So if I wanted to start walking, what I could do is just have the instantaneous capture point start moving in this direction. So I have my foot here until it gets about there, and then take a step here. So that then it would move in this direction till, yeah, I could wait till about there, and then I could step here. So that would then push in that direction. Then once it gets there, I could step here, which would push it in that direction. And once it gets about there, I can step here, which would push it in that direction. And once it gets there, step right there and come to a stop there. So that's planning using instantaneous capture points. So, whereas if you were trying to figure out center mass paths, it would look more, let's see here, you kind of have to do it more like, kind of do this sort of thing. Really, really complicated equations.
So, right now, we don't have an exponential in here. Do we have an equation for the hyperbolic that it makes? Or is it just?
Well, that's what I wrote a few slides ago with the hyperbolic sine and cosine. That's what this curve would be. And then this path as a function of time would just be its current position times e to the square root of g over z naught.
Now, that's the equation I'm interested in, the E thing.
Yep.
Because as a draftsman, I can graphically relate time and space using the time constants and just draw these
Well,
things
just
by
write
hand.
it one more time then. So
Okay.
so it was that p dot,
Which is x
Sorry,
minus x
sorry.
desired, or what is P?
p of t equals p of
That's
0.
XICP minus
E.
X foot.
Minus x
The square root of g over g. And as it squares g, as gravity is increasing, it grows faster, right?
So P T equals P minus.
If you have no gravity,
And so this is the same as saying XICP.
let's do it.
Just go into space.
Yeah. Then walking's easy.
Now there's a whole another series of problems, such as
Well.
what gets you back to whatever you push off of.
Jetpacks.
So, okay, so here's the.
With
here's
limited
the
fuel.
equals
Magnets.
T equals x foot
But the
plus
distance away from something drops so drastically. You're really far from something the magnets are.
Okay, so this is the ICP equation. So XICP, and again, these are XY vectors, is x of the foot plus the distance between the ICP and the foot at time 0 times e to the square root of g over z naught times t. All right, any questions?